When we look at the formula for linearization, it has exactly the same ingredients as a formula for a line. The key thing as a difference is really how we express the various constants. In a generic form for a point slope line, we have the slope m, but if we're using derivative terminology, then the slope comes from the derivative. If we have a reference point for x, that's our a value, that stays the same. But if we actually looked for what the height at that reference point was, let's say a is here, how would we know what the height of the function value was there? Usually we'd call it c if we didn't have any other information. But if we actually have a formula for this curve, then it's also computable by just saying what's the function value at a. So with this terminology, we're using functions and derivatives to complete or fill in what was essentially the formula for a straight line through a point that you would have seen earlier in your career. The subtext is the actual function is curved. So when we draw or compute this tangent line approximation, we can see that the blue line and the green line are similar for a little while. So as long as we don't move too far away from a, things are good, the approximation is solid. But of course, if we keep following that green line for a long ways away, the actual curve may get quite different. So this is an approximation where the blue line is being mapped to the straight green line, and they're approximately the same in the neighborhood where we build our estimate. They get worse and worse as estimates as we go far away. Having just seen this formula, it's worth remembering that we also saw another relationship based on Leibniz notation, where we said the derivative dy dx is approximately the same as delta y over delta x, where we actually have changes in x and y. These are both linearization formulas. That can be confusing initially until you realize they're exactly the same formula. There's nothing different between these because it's easy to convert from one to the other. Imagine we have a reference point A and we go out for delta x here. The idea is that new point is some x value. If we use that, let's take a look at this formula here. Our function is approximately equal to f prime of a, x minus a plus f of a. Well, if we're building our estimate around a, the distance from x to a is exactly what delta x is. So that's delta x. So f of x is approximately the slope times delta x times plus f of a. Well, let's bring this to the other side. Minus f of a times delta x. What does this value represent? Well, f of a is the coordinate in the y direction where we're starting. The other value, f of x, is what we get as a height later on. That's our f of x. It's actually the curved value, but we'll stick with the straight lines for the purpose of this diagram. And if you think about what the difference between here and here is, well, in a slope diagram, we call that delta y. And that is the difference between the endpoint f of x minus f of a. So that is delta y. And one last step. Here's our relationship. All we do is divide by delta x. The slope at that point, f prime of a, so whatever slope we get at the reference point we base ourselves at, can be approximated by the rise over run. If I make a change in x, I'll get a certain change in y back. That formula, if we work backwards and just decompose these changes in x and changes in y, give us the exactly equivalent straight line approximation formula that comes or is more easily thought of as basing ourselves at a point and with a slope. But they're the same formula under the hood. There's nothing new. You can memorize one and transform. You can memorize both, as long as you recognize that they really are the same thing. Let's use that in an example. Looking at the population of Canada, currently around 33 million, and increasing at a rate of 300,000 people per year. Let's add some interpretation to that, where we say now as t equals 0. This 33 million would be the population now, and this rate would be p prime of 0. And let's pick units of people just to keep it simple. 33 million. So the value is 33 million. The slope is 300,000 people per year. And so what we'd get is the population at any time, t years in the future, or years from now, will be equal to, well, we're gaining 300,000 based on how many years away from today. That's going to be our change in population, but we start currently at 33 million. So we now have, if t was 0, we would get exactly 33 million. As t gets bigger, the more we add to t, the more influence this growth has on our population. And we just note that it's going to be an approximation because we're not going to always have this 300,000 per year, but for small time intervals, it's probably a good approximation. Let's use that to predict into the future 2 years, so t equals 2. The population 2 years from now is going to be approximately equal to 300,000, and this t is the variable that we're subbing in for now, so that's where we put our 2. You could have simplified away the -0 if you felt like it, that would have been fine. So we're going to be at a population of 33,600,000 people approximately after 2 years, or 2 years into the future, using our derivative as a prediction tool. When we make these predictions, are we getting an underestimate or an overestimate? Let's just do a quick sketch of what that means. We predicted our 33 million today. That was an exact value. This will be in millions on this axis then. And t is on this axis. And we knew the slope. And what we just did with our linear model is we basically assumed that things were going to keep going in that straight line manner forever. What does the actual population do? Well, what we're told is that the Canadian population is actually growing exponentially. So not as a straight line, but it's going to curve. Think about that for a moment and ask yourself, will that previous population estimate be an underestimate or an overestimate? When we follow the straight line, are we getting a low ball or an overestimate for the actual population in 2 years' time? Well, this involves knowing what the exponential growth graphs look like. If we're growing exponentially, it's going to be a curve that can look like a straight line for a while, but it's going to curve upwards. It's going to be concave upwards. And so this is going to be our prediction. This value here is the actual population that we're going to achieve in the future. And so our prediction is going to underestimate the actual population. If we know that our curve is exponential, then that means it's concave up, and this straight line approximation is going to stay too low compared to that concave up graph. For these types of questions, that's the key ingredient. The straight lines are baseline, and you have to determine whether your curve is going to be curving upwards, concave up, or concave down. If it had been concave down, we would have had an overestimate for our population. Here, though, it's concave up. The actual would end up higher than the straight line. So our 33,600,000 would be a little bit below the actual population in 2 years.